Welcome to this introduction to synthetic map. In this video, we will explain what is synthetic map and how it can be used in your organic chemistry studies. Organic synthesis is concerned with the transformation of one functional group into another using chemical reactions. An example would be the reduction of an aldehyde by sodium borohydride as shown here. A typical organic chemistry course might comprise anywhere between 100 and 200 of these transformations. Learning them all can be a formidable task. Usually, a course in organic chemistry will systematically explain how each group can be made, or which reactions that functional group can undergo. For example, here we see various ways to make a primary alcohol, or which reactions that functional group can be used for. This process is repeated systematically for each of the common functional groups. However, this can often lead to the different groups and reactions being mentally segregated rather than seen as an integrated holistic network. For the new student of organic chemistry, this can make applying these many different reactions to perform an organic synthesis particularly challenging. How can a beginner possibly know what intermediates and reagents are needed to arrive at a target compound when multiple transformations are required? This is where the synthetic map comes in. The synthetic map is a visual map of all the commonly encountered functional groups in organic chemistry. You can think of it as analogous to any other map that lays out all the major destinations, which in this case is all the different functional groups. It then shows you all the possible connections between them, making arriving at any destination a simple and straightforward process. To get started, go to syntheticmap.com and go to the Maps tab. There you will find all the different types of synthetic maps. There is a basic map designed for undergraduate students, which is available in various languages. There is also an advanced version aimed at the postgraduate level, which covers more advanced reactions. For this demonstration, we will select the basic organic map in English. There is also a printable version of the map, which you can also access from the web page. We will now explain the various features of the map and how it is organized. We will then give examples of how you can incorporate its use into your organic chemistry studies. The map is organized so that the most used functional groups are situated at the center, and the less common groups are located towards the peripheries. At the center of the map is the alkane functional group. It is surrounded by what we consider the three most important functional groups: alcohols, alkenes, and the carbonyl group. It should be noted that the representative structure for each functional group is for illustration purposes only and does not attempt to capture the changes in the number of carbon atoms between the different transformations. Each of these three core functional groups is adjacent to a colored area or zone. The first zone consists of the alcohol and related functional groups with sp3 hybridization. The reactions covered here are nucleophilic substitutions and elimination reactions. Moving in a clockwise manner, the second zone comprises the alkene group and all the related unsaturated compounds with sp and sp2 hybridization, such as alkynes and aromatic ring systems. Here, the main reactions covered are electrophilic addition reactions to alkenes and alkynes as well as aromatic substitution reactions. The final zone comprises the groups and reactions related to aldehydes and ketones. Since this covers a large amount of reactivity, it can be divided into two separate sections. In the lower part are situated carbonyl compounds that act as electrophiles, while at the top, we find examples of reactions in which the carbonyl group acts as a nucleophile, such as in aldol-type reactions. The reactions between the main functional groups situated around the central triangle allow us to easily pass from one zone to another, allowing connectivity between the three zones. On the right side of the map, you will find a guide that explains the meaning of each design element within the synthetic map. We will briefly cover each item one by one and give examples to clarify the various points. You will see that the functional groups are connected by three different types of arrow. Each arrow has one or more numbered circles on it that corresponds to the reaction that allows for the transformation between the two functional groups it connects. The most common is a thin black arrow that denotes a reaction that results in a functional group interconversion. You click on the numbered circle, the application will open a new page that explains that particular transformation in detail. This includes a visual representation of the reaction, a brief explanation, and the reaction mechanism. Alternatively, if using the paper version of the map, the number allows you to refer to the corresponding reaction on the back of the map, allowing you to find the reagents needed for the transformation. Blue lines are used to represent carbon-carbon bond-forming reactions and distinguish them from standard functional group transformations. These reactions are some of the most important in organic chemistry, as we cannot construct the carbon skeletons of molecules without them. Therefore, when the number of carbon atoms in a molecule increases, we must incorporate a blue arrow in our proposed synthetic route. Finally, the thick black arrows represent reactions between functional groups from the different zones. As there are multiple ways to carry out the same transformation, the thicker arrows represent the relative weight and importance of these processes. In most instances, these thicker black arrows work just the same as the standard black ones, showing the direct transformation of one key functional group to another. For example, the transformation of an alcohol to an aldehyde can be carried out with PDC. However, in some instances, the reaction represented by a thick black arrow will not lead to the directly indicated group, but instead to one in the adjacent zone. For example, if we treat a primary alcohol with a Jones reagent, the oxidation gives the corresponding acid. When this is the case, the circle has the functional group next to it to indicate which is the endpoint of this reaction. Another example would be the removal of a functional group by reducing it to an alkane. There are many ways to do this, starting from different functional groups. If we attempted to connect all these groups directly to the alkane, the map would soon become messy and incoherent. Instead, if we look at the black arrows, we see from which functional group from that particular zone the reaction represents. Certain transformations will give the same functional group, but with different regioselectivities. For example, converting an alkene to an alcohol can give rise to two possible products, one with Markovnikov selectivity and one with anti-Markovnikov selectivity. To mark this difference, the reactions on the map are indicated with the letters M and AM. Similarly, the letters Z or H are placed next to elimination reactions to indicate the regioselectivity. In some instances, functional groups can be found in more than one zone of the map. For example, an ester can be formed via a nucleophilic substitution reaction here in the first zone of the map. Since this compound can now be considered a carbonyl compound and will undergo the chemistry found in the lower left part of the map in zone 3, there is an indication on the map that we can jump from zone 1 to zone 3. Another feature of the map is the mechanism indicators. If we click on one of these, we access a description of the general mechanism represented by this process. One of the most important pieces of information about any functional group is its type of reactivity. In other words, whether it acts as a nucleophile or an electrophile in a reaction. This information is displayed visually on the synthetic map, with nucleophilic functional groups in blue and electrophilic functional groups in red. Another vital piece of information about any functional group is its pKa. This information is essential to select the correct base for a reaction, and is indicated next to the structure. The synthetic map can be used in different ways, depending on the type of problem we want to solve. In its most basic form, the synthetic map can act as a repository for all the reactions you need to know as part of your studies. Instead of learning the reactions by rote, the map can be used as a dynamic tool to locate the functional groups on the map and find the required reagent. By having access to this resource, you should be able to answer most questions you will encounter in a basic organic chemistry course. With practice, the information will be assimilated naturally, and soon, it should not be necessary to refer to the map or your notes and textbook. If we want to carry out a synthetic transformation that requires more than one step, for example, if we intend to synthesize the following thiol from the illustrated ketone, How can we determine the reagents and the intermediates necessary to carry out this sequence? We first identify the initial and target functional groups. One possible route between these groups would be to convert to the alcohol, then to an alkyl halide, and finally to a thiol. We can then write out the corresponding intermediates for our molecule. We then have to simply click on the relevant reactions to find the required reagents, which we then add to our scheme. What happens if we want to arrive at the same product, but instead start with an aldehyde? As we can see, one of the carbon atoms is missing, which means we need to incorporate a C-C bond-forming reaction into our synthesis. In other words, a route that includes a blue arrow. One possible option is to add a Grignard reagent, which would give us the same intermediate as in the previous example. We can then follow the same steps as before. We then write out the full scheme and the required reagents. A third possible option for this compound would be to convert the aldehyde to an alkene by adding the required carbon atom and then to the alcohol. The remaining steps would then be the same as before. These examples demonstrate the versatility of the tool to propose multiple synthetic routes to the same compound and show that there is usually more than one correct solution. In conclusion, we hope that as you use the synthetic map alongside your studies, you will naturally develop a comprehensive understanding of all the important functional groups and their reactions in both an effective and enjoyable manner. To begin your journey in this new way of conceptualizing organic chemistry, go to syntheticmap.com